I've been talking about this in 4 different classes because AP1 and mechanics are both starting Newton's laws. And I fail every time to really help you guys appreciate what it is when we talk about Newton's laws. So I'm going to try a slightly different tact. You want to know what you're going to have to know for the next test. I want you to understand that what we're learning here isn't about tests. Newton's laws as a set of equations go are really poor equations because they're not intended to be equations. So you guys who have learned about F equals ma and stuff like that, that's not what we're going to be dealing with here. F equals ma isn't an equation. Not in the way in which you learned it in middle school. It's important that you understand that these are laws, and they're about our observation of the known universe. So when we talk about them as laws, there are no exception to these laws. If you observe something, these laws must apply, and they must apply completely without exception. So since I'm not sure you understand where I'm going with this, your observations and experiences on the earth have made you not particularly well prepared to deal with Newton's laws. The best example of that is anytime you have thrown or pushed or shoved something, it has eventually stopped moving. Before Newton's laws, there was an understanding that all objects that were given a push were imbued with a certain amount of impetus. It's a Greek idea. And that objects would move until they ran out of impetus and then immediately drop to the ground. Now that doesn't perfectly fit with any of our examples of what happens when you throw stuff. But it was the prevailing theory because everything eventually stops moving. Newton's first law throws all of that away. All of it. You've heard the phrase before, the colloquialism. Objects in motion tend to stay in motion. You heard that phrase before? It's a colloquialism because it's missing some pieces. Let me tell you the way I would like you to know it. An object will maintain its state of motion or state of rest unless acted on by an external, unbalanced net force. There's a lot to unpack here, but get it down first. Let's start with this phrase, state of motion, state of rest. This is speaking directly to velocity. I can replace all of that with the single word velocity. That an object will maintain its velocity unless acted on by an external unbalanced net force. Which means if you throw something, it will continue moving forever unless acted on by an unbalanced external net force. How would you ever know? Everything you've ever thrown has always stopped. Why is this believable? Well, you're asking the wrong question. The question you should ask is, what made the object stop? There should have been something that caused it. You see, the law is telling you that if your object changes its motion, something caused it. It's saying in the absence of something causing a change, then these conditions must be true. Notice it doesn't say that no force is acting on the object. It's saying that all external forces are balanced on this object, and therefore they sum to be zero, so the object's motion doesn't change. That's what this law is stating. It's not up for debate. It's not contrary to what you observe. It's saying that under the conditions where the net force equals zero An object's state of motion will not change. This is the mathematical way of writing it. It's a set of instructions. It says that if you believe the first law applies in some situation, then when you add up all the forces on the object, taking into account the direction of each force, they must sum to be zero. That's what the instructions are. The equation part isn't an equation you apply. It's a set of instructions you can use. Therein lies the difference. But for that to be true, you have to know, whether the first law applies in the situation you're observing. You see, Newton's laws require a lot of you. They require you to judge a situation and decide whether it's a first law situation or a second law situation. The first law covers situations in which the object is not changing its motion. Now, the second law, of course, is going to cover the situations in which the object is changing its motion. It says if If an object is experiencing an unbalanced external net force, then it will accelerate. Its acceleration will depend on its inertia. Now, I could have said that if an object is accelerating, then it must be experiencing an unbalanced external net force. I could say both of these laws in the contrary. Although they are if-then statements, you can say them in the opposite order. But the second law is about acceleration. It's about changes in motion. But it says more. It introduces a new word, inertia. Now, inertia is a word that you likely have a definition, but I want to be very clear. The real definition of inertia is circular, meaning inertia is another one of those intrinsic properties. Its definition is based on observation. Inertia is an object's resistance to changes in motion. It's a definition of inertia. Again, inertia is an object's resistance to changes in motion. Now, to clarify that a small amount, I want you to be aware that inertia is a concept that I come back to a lot during the year. Because if you understand inertia, you can understand quite a bit of physics. You're already aware of inertia, though. I don't really think I have to define it too well. You know that big objects are harder to move than small objects. If you're a little person and you walk down the halls of this school, big people have bumped into you, you've moved more than them. Why? You have less inertia than they do. If you're a big person, you've been bumping into people, well, you're a jerk. Try and avoid people. But you've moved less than them. I mean, big trucks on the highway, you get out of their way. Right? You don't toy with them. Because no matter what, you will lose. There's a reason. They're bigger. They have more inertia. If you don't believe me, who wins? Your car or a bug? In that competition, I'm pretty confident it's the car. I've yet to see the bug that has stopped the car. Inertia is about size, but it's a measure of an object's resistance to changes in motion. For the longest time, we didn't fully understand inertia in the way we do now. But now we know that the same thing that causes inertia causes gravity, which means we know that inertial mass and gravitational mass are the same thing. We didn't always know that. So the intrinsic property mass causes two things in nature. It causes inertia and it creates gravity. So we write this as the sum of all the forces must equal MA. It's the set of instructions that are employed if you know your problem is a second law problem. Now, Newton's second law is interesting because it has two parts to it in a way that Newton's first law doesn't. The first part of Newton's law is about whether an object is accelerating or not. If you observe an object accelerate, it must be experiencing an unbalanced net force, whether you know what force is doing it or not. There have been plenty of examples of observations of astronomical objects that have changed their motion in ways that were unpredictable. And it wasn't as though the person watching said, whoa, there must be new science here. What they have to state is, whoa, there must be something pushing on the object that I can't see. Has to be. Newton's second law is invariant. So if a planet's orbit suddenly changes or changes in a way that's unpredictable, something must be out there applying a force to it. Several planets have been discovered because of this. Neptune is one of them. Neptune was discovered because Uranus's orbit was changing under observation. They conjectured there must be another planet out there. Lo and behold, with enough observation, Neptune was found. So Newton's second law is one of those things where if you observe an acceleration, then there must be an unbalanced force that causes it. You don't have to know what that is, but it has to be true. Interesting, be careful about acceleration. We're not talking about just a change in speed. It's any change in speed and or a change in direction. Remember, acceleration is any change in velocity. So it has to include changes in direction and changes in speed. So it's not just about speeding up or slowing down. It's about things that travel in a curved path. The moon must be experiencing an unbalanced force. It has to be. Its direction of motion is always changing. The only way that would happen is something is pushing on it all the time. And of course there is. The Earth is. In the same way that the Earth must be experiencing an unbalanced force. Of course it is. The sun is there. All these things are applying an unbalanced force. And that's what's causing the acceleration. But the second part of the law is that your acceleration is balanced by how much inertia there is. For the same force, two different objects can behave differently. An object with a lot of inertia is not as affected by an unbalanced force. It's not as effective at moving the object. While an object with very little inertia might be more affected by that unbalanced force. The effectiveness of an unbalanced force is what is determined by inertia. That's why inertia is an object's resistance to changes in motion. Now, those are Newton's laws. In the grand scheme of things, I overtalk them. And whether you wrote it down or not, I gave you all sorts of things that you need to know. I was trying to be careful and diplomatic about all the things I indicated, but every piece that's there is something you need. Now let me just stop and move to the side for just a minute and argue that eventually you'll have to solve physics problems that I give you based on this. Please be aware that the only thing Newton's laws can successfully tell you is the size of a force, not even size, a force can tell you the size and direction of a force and or the size and direction of an acceleration. That's all Newton's laws could tell you. The size and direction of a force and the size and direction of an acceleration. That's it. But keep in mind, once you have an acceleration, you have a method for determining changes in velocity. And once you have velocity, you have methods of determining change in position. All the kinematic stuff applies once you have an expression for an acceleration. You see, understanding how forces operate gives you all of motion because it gives you acceleration. So how are we going to, using Newton's laws is a different thing. What I'm going to ask you to do when it comes to Newton's laws is to understand that problems can be analyzed without having question marks. Meaning you can look at a situation and you can apply Newton's laws to that situation to analyze it. The analysis itself will lead to a solution if you're looking for a solution. But if you just want to analyze something, Newton's laws will provide an analysis. For the next couple of days, there'll be no question marks at the end of our conversations. I'm just going to say, analyze the situation that I provide for you and tell me what you know about it. And your job will be to apply this series of steps. I do have a series of steps, but this is not like kinematics. It's not as procedural. You're going to have to bring something to the table. This year, 4 steps. I'm looking at 4 steps, 4 things you will have to do to analyze the situation. So I'm going to give you your first situation. Your first situation is to analyze Iron Man. He's sitting on the table. We're going to use Newton's laws to analyze Iron Man. Again, all that this can do is either tell us an acceleration or tell us a force. So let's see what the analysis of Iron Man can tell us. In any problem that you're facing, that you're going to use Newton's laws for analysis, the first thing I'd like you to do is to contemplate whether you believe the first law applies or the second law applies in that situation. Is this a first law problem or a second law problem? Now, when you're making this decision, you probably should be looking at acceleration. If your object isn't accelerating, it's probably a first law problem. If your object is accelerating, it's probably a second law problem. If you don't know, you have to assume it's a second law problem until you prove it's a first. And if you don't know whether it's accelerating, then it's likely you're trying to figure out what forces are acting on the object to see if it accelerates or not. But be careful. First law problems apply to all problems where the velocity is constant. Don't assume first law means not moving. First law means not accelerating. Don't fall into that trap. I agree. This is likely a first law problem. He is not accelerating. He's just sitting there. Would you guys agree with that? All right. The second thing that I will ask you to do, and by far the most important thing to get right, is to draw a free body diagram. I can't emphasize enough how you need to get this right. If you get this wrong, you can't get anything else right after this. So you really have to do a great job of nailing this. Drawing a free body diagram is also something that you need to be good at presenting to somebody who's going to grade it. So everything about this is rulers, careful attention to detail, appropriate scale, all of that applies. And I'll explain what a free body diagram is supposed to be, but understand that you will need a ruler. The meter sticks are probably not the thing. Bring in a freaking ruler, something straight that you can draw straight lines with, all right? Because otherwise you're gonna be hitting people in the head with the meter sticks you have out there. So bring a straight edge from now on, please. You will need it for everything we do for the next couple of weeks. There's a series of steps to draw a free body diagram. They're very easy, but you have to do them exactly as they are described. You can't veer outside of it. The rules are specific, and you are graded based on how well you do this. A free body diagram can only deal with one object at a time. So step 1, reduce each object with mass to a single point. Reduce each object with mass to a single point. We remove all of the extension from the object and reduce the object to a single point. If there's 5 objects, they must be evaluated separately, each object getting its own point. We will do up to a 3-body problem. So you need to be able to study at least 3 bodies. For the first semester, we assume our objects have no extension, which means all of the forces act at the center of the object. This dot represents the center of the object. Second semester, we'll add extension to our objects, meaning we'll understand that pushing at the top of an object may cause it to fall over. Pushing at the middle of the object might be more effective. We'll understand why that works second semester. But first semester, we will assume that all of our objects can be treated as a point. Next, we're going to evaluate forces. Each force is represented as an arrow that starts at this dot and extends in the direction of the force. Each force is represented as an arrow that starts on this dot and extends outwards. The size of the arrow and the direction matter. All right. What you need to do next now is identify the types of forces that could be acting in your problem. What I want to give you is a kind of a set of things to look for here. We can break these forces up into 3 categories. So I want to start by considering the fundamental forces. So, the fundamental forces. Now, we talked about the fact that there are 4, but in this class there will only be 1, weight. So for this, we're just talking about the weight. Weight is the force of gravity. So to handle that, I look at my little guy there. If my little guy is on the Earth or near any planet where it's experiencing the force of gravity, then there should be a force drawn to indicate the force of gravity. This is an easy one, kind of a no-brainer actually. And more importantly, because you know you're going to have this force, I would use this force as your means of establishing scale. And I know you might not appreciate what I mean by that, but you have to draw this force in. So you should be drawing it in such a way that you understand that the length of the arrow is something that's going to be relative to other forces you are going to draw in the future. We are deciding whether it's a first or second law problem. We probably established that this is a first law problem yesterday because we know the guy's not accelerating. So for every down arrow is going to have to be an up arrow, and every left arrow a right arrow. So you're establishing scale with your first one. The length of the arrows represent the size of the forces, and you will have to be aware and cognizant of that. Now, we won't have any other fundamental forces, but I do want you to know that there's other ways to write this. Your textbook would probably write F with a subscript G, labeling all forces with an uppercase F and then subscripting them for the type of force they are. I think that's a little pretentious and can get quite cumbersome. What if you have more than one normal force or more than one tension force, and every force starts with an F and then a subscript, and then now you have a number? You understand that can get pretty cumbersome pretty quick. So I tend to use just the first letter of the word, and if there's more than one, then I will subscript them. But you have to use the lettering that they give you in the problem. So also be aware of that. It also could be F sub W. I've seen that before too. You choose a book. They might try any one of these things. When we're done with the fundamental forces, we go down to the contact forces. These are obvious because for contact forces, there must be something in contact with the object to apply that force. And I'm really only going to talk about 2 of them, but there's a third I'm going to bring up. The first contact force is what I call the normal force. So we look at our object and we ask ourselves, is the object in contact with any surface? And of course, in this case, it is. There's not much contemplation that has to happen here. If it's in contact with the surface, touching any surface at all, then a normal force is acting on the object. And a normal force must be drawn so that it is perpendicular to the surface. That's what the word normal means. So if the object's touching a surface, you must then go and draw a force or an arrow that is perpendicular to that surface. And again, I'm not drawing this force haphazardly. I'm going to draw an arrow that is roughly the same size as the weight, because I'm looking ahead. I see no strings attached to this guy. This might be the only other force pushing upwards on him, and I know that I need to strike balance because it's first law problem. Normal force, of course, There are some books that will do F sub n. I'm not. I'm going to just do a capital N. Now, there are tension forces. But for there to be a tension force, it'd have to be a string or a rope or something attached to this guy. I don't see anything like that, so I'm not going to worry about tension force. However, be careful about tension forces. Be careful. If there's tension in your problem, look at what that string's attached to. First semester, when we deal with tension, the tension is the same throughout the entire length of the string. So if it's connected to more than one thing, then the tension at both ends is the same. It's something to think about. Perhaps 2 examples from now. Now, the third one isn't a category of force I talked about, but it is plausible that your problem will say there is an applied force acting on the object. They might just say, this is happening, and not categorize it at all. Applied forces will boil down to one of these, but don't stand on circumstance and don't stand on ceremony. If you know a force is acting but don't know how to label it, at least draw it in there and give it a label anyways. Now, this one I don't think we have to worry about that, but be on the lookout for applied forces or forces to which you don't have a good category. But don't invent them either. Okay? They're going to break up into one of these categories. The last thing we have to look for, resistive forces. Resistive forces. There are 2 that will generally come up in this class. Friction. I use lowercase f for friction. And drag. I don't have any specific thing for drag. Friction is a force that attempts to prevent one surface from sliding past another. It's a definition of friction. It's a resistive force that attempts to prevent one surface from sliding past another. It's sometimes hard to know whether friction is a part of a problem or not. It might take some careful consideration. But again, friction is a force that attempts to prevent one surface from sliding past another. It must act parallel to the surface or along the surface. Interesting thing about friction, it can act on objects that are at rest or moving. Friction can hold something in place, or it can act to slow something down and stop it. So there are different types of friction. But ultimately, if there's no contact with the surface, there's no friction, which means there has to be a normal force for there to be a frictional force. That seems obvious now. It might be less obvious later. Also, it could be that normal forces have something to do with friction. So pay attention to that. Normal forces and frictional forces have to be perpendicular to each other. They have to be, by consequence. Now, drag forces are a little different. Drag is a force that tries to prevent an object from moving through a fluid. Air, water, maple syrup. A drag force acts against velocity, or acts in the opposite direction of velocity. So an object has to be moving to experience the drag force. So objects at rest don't experience a drag force. Now, that being said, drag forces can change direction all the time, especially if the object is changing direction all the time. Imagine throwing a ball through the air. If it's traveling in an arced path like a projectile, well, the drag force is always changing direction. But even something as simple-minded as throwing a ball straight up and having it come back down, the drag force acts downwards while the ball is traveling up and acts upward when the ball is traveling down. If you think it through, that tells you that it takes the ball longer to come down than it did to go up, right? Because friction was slowing the ball down to stop it. But then, drag was slowing the ball down to stop it. But then drag was trying to prevent the ball from coming back down by acting upwards as the ball traveled downwards. So be careful in your application of drag. It might change partway through your problem. All right, that was step 2. Any question about step 2? We have drawn in all the arrows to represent the forces for our object. Our object only had 2. But I've gone through all the possibilities that you are likely to face this year. There are other forces. This is not an exhaustive list. Bernoulli's force, the buoyant force, the electromagnetic force. There are a lot of other forces. And although I only named 3, I could probably name more. Let's go on to step 3. Draw in a coordinate system. Draw in a coordinate system. This is something that seems so ridiculously easy now, but I have students who screw it up consistently every year. And it tends to be the same kind of students. So in this room, there's about 3 of you who I think have the potential to make this mistake. So let's just stop right now and you put something down that will prevent that. A coordinate system is an XY plane, which means X and Y have to be perpendicular to each other. Have to be. So we talk about a coordinate system, we're talking about an XY plane. Now, we could do this in 3 dimensions. I could say X, Y, and Z, but our problems will be no more than 2 dimensions for now. Now, don't just draw in any coordinate system, because ultimately, any force that is not aligned with your coordinate system will have to be broken up into components. Our math only supports 1-dimensional algebra. So you want to try and reduce the amount of trig you have to do. However, you really have 2 priorities to keep in mind. And I'll put them in order of importance. In order to solve a problem, if you want to make the problem as solvable as possible, then make the positive x direction the direction of the acceleration. Positive y direction works here too, but let's just say make one of the positive directions the direction of the acceleration. That should be your first priority. Your second priority is to line up as many forces as possible with the axes. You may be limited as to what you can do, but that should be your goal. Because any off-axis forces will have to be broken up into XY components. And you'll have to take those forces and find out how much of them act in the X direction and how much of them act in the Y direction. This is step 3. Now, for the example we have at hand, we have a ridiculously easy example. It's 1-dimensional, so I'm not really going to worry too much about drawing in a very carefully constructed coordinate system, but I am going to draw in at least a 2-dimensional one, even though my problem is 1-dimensional. All right, onward to the last step. Any questions yet? We made a decision at the very beginning of this problem where we said that this is a first law problem. Once we're here, we're committed. Now you can change your mind after you've drawn all the forces if you feel like there's a reason to change your mind, but I still see no acceleration over there. So I think this is a first law problem. So step 4 is apply Newton's law. In each direction. That means x, y, and z for 3 dimensions, but we only have generally 2-dimensional problems, so I will say net force in the x direction equals 0, and net force in the y direction equals 0. This is the first law problem, so they're all 0. If this were a second law problem, then net force in the x direction likely will equal ma, and net force in the y direction will equal 0, because we would have obeyed the first priority, which was to line up our system with the direction of the acceleration. Now, just a reminder, this is a set of instructions. Add up all the forces, taking into account their direction, and set them equal to 0. That's what these instructions state. That's what I mean when I say apply Newton's law. Now, we have no forces in the x direction, so there's nothing for me to do here. But in the y direction, there are 2 forces. There is a normal force in the positive y direction, and there is weight in the negative y direction. I must add them together, taking account their direction, and set them equal to 0. Now, when you reach this step, you should be left with at least 2 relationships, one for each direction, that could then be used to solve your problem. This is the analysis. The process doesn't depend on what the question is. The process is how you evaluate a system using Newton's laws. It's not about physics problems. It's about how Newton's laws actually get applied in the real world to deal with things that you're observing. Now, you're going to have to solve physics problems using this. But I'm trying to tell you this is something bigger than that. So we're going to analyze some problems. I want you to apply this series of steps to do so. We're going to start simple, but I think you can imagine I'm going to try and make them more and more complex as we go. I have little cards I'd put out there, but they've been since scattered. And the way today has gone, clearly from my story earlier, I just don't feel like working diligently to make it all happen so magically. The whiteboards didn't work out the way I wanted. Panache. So there's the book, and Sheldon got the old gout here. There's the hand-ish. Eek. All right. Would you say this is a first law problem or a second law problem? I think the book was, well, I was doing everything in my power to keep the book in place. So I think a first law problem. And this question's gonna come up. So I'll remind you, you reduce each object with mass to a dot. There's only one object here, the book. So I will start by taking and reducing my book to a dot. Is there a fundamental force acting on the book? I think we can all agree that the book has weight. So I'm going to take and draw a downwards arrow that will represent the weight of the book. And I will label it appropriately. A vector without a label and a force diagram will be given no credit. So pick your labels, stick with them. Is the book in contact with any surface? Yes, it is. I don't have to think very much about this. If it's in contact with a surface, the surface applies a force that is perpendicular to the surface. So that's got to be a force this direction. It must be. I don't get a choice on the direction of this force. So this is a normal force from the wall. Now, is there any other force acting on the book? Is it attempting to slide past a surface? Is there any reason to believe that if I wasn't there, the book would slide down the wall? I think there is, right? In fact, something has to push upwards on the book to keep it in place. I think it's not unreasonable to suggest that there must be an upward force on the book due to friction. If you noticed, I was careful to show you that I was pushing just horizontally onto the book. Which brings me to my last force. Me. I pushed on the book. How do you want to address this one? Yeah? Be an applied force. You could treat it as a normal force. Don't stand on ceremony here. I pushed on the book. Normal forces are pushing forces. You'd be okay writing normal force. Maybe normal force from my hand. Or F applied. I don't really care, but I definitely pushed on the book. What you have to realize is that you need to draw it this way. Don't draw it with the point pointing at the dot. All forces are drawn from the dot away. And I don't care whether you draw it as an applied force or normal force from a hand. I don't really care. I was not pushing the book at an angle. I could have tried. I did not. Now, I believe we've encountered all the forces acting on the book, so we need to apply a coordinate system. I think that part's pretty straightforward, and I'm going to kind of blow through that so we can get to our next example. I'll start with a X and Y system that is aligned with as many forces as possible. And I think that's going to be all of them, which makes this pretty convenient. So there's my X and Y. I'll make this the positive X direction and this the positive Y direction. Have I veered at all from the set of steps that I talked about from the beginning? No, I am applying them very cleanly, very clearly, the same way this time. And I will do the next portion, which is net force in the X direction equals 0 and net force in the Y direction equals 0. So I will now follow the set of instructions that are instigated here. Add up all the forces in the X direction, taking into account their direction, and set them equal to 0. So I will have the force applied minus the normal force from the wall and set that equal to 0. And I will take the frictional force minus the weight of the book and set that equal to 0. I have created two relationships that could be used to perhaps solve for something about this problem. Yep.
And does it matter what order, does it matter what order you
I don't understand the question.
Like, I use F minus W.
Well, it doesn't matter except that I labeled the direction I called positive. So I would want you to be consistent with your labeling. All right, because I would like to finish this one. It'll be hard, 6 minutes. I have a pulley with a rope on either side, and there's a person on the right holding onto the rope and a person on the left holding onto the rope. I believe this problem has 3 different objects: the pulley, the person on the right, and the person on the left, so I think you're drawing 3 different dots. All right? What you should do So let's start with the guy on the right, since that's probably the easiest place to start. Can we agree that person on the right has a downward arrow acting on them? Did you do a one of those? And since I think we can all probably say this is a Newton's first law problem, you probably drew a upwards arrow of equal length. Now, handling this guy over here on the right, did you draw their downwards arrow greater? Because I would have. But here's the next question. If you drew a tension on him, that makes perfect sense. He's holding onto a rope. But the tension should be the same size as the one on the other side, which means that that's not enough for them to be at rest. But they are in contact with a surface. Did you draw a normal force? Now, you should have, but there's debate on how you might want to do this. You have choices, and let me, because I have a moment, kind of talk to you about the two choices. You're welcome to draw this force side by side. That tends to be how I do it, putting them both on the dot, everything starting from the dot. But there's a group of people who kind of like them stacked like this to show that there's the same length up as down. I don't care which of these two you do. Still needs to be labeled. I'm just going to tell you that I tend to do it this way. But I don't care which way you do it. All right? Yeah, I know you guys are scared too, because I could say anything at this moment, and you're worried it'll be you that I'll make fun of. So here we go. I don't want to spend a lot of time here, but I do want to talk a little bit about how you would be graded. And I'll start by saying you would be graded as doing something wrong if you had not made these two weights of different size. More importantly, you need to make the guy on the left heavier than the guy on the right. And you need to make the tensions the same length, pointed upwards, because the tension everywhere in the rope is going to be the same value. At least it will this semester. So when I start drawing these arrows downwards, the first one I'm going to draw, and I should use a ruler, and I'm not, is tension. And there's going to be two of them. And they should be the same size, and they should be the same size as these tensions. It's all the same rope. Now, for the next one, you can be forgiven with whatever decision you made here, because you have nothing to go on the size of the weight of the pulley. But if you have nothing to go on, don't worry about it. They're aware you have nothing to go on. Just draw on the weight of the pulley. Now, like I said yesterday, you can stack these arrows if you want. You can draw them side by side. I don't care. Make them legible and clear. But we're not done here, right? Net force equals 0, so there should be another force drawn in. And that's going to be a force that is upwards to hold the pulley in place. I can't draw an arrow tall enough that would account for the 3 arrows that are downwards. So I'll draw it all the way up to the top of the ceiling, but the truth is my scale is off. Now, I totally pooped on somebody in 6th period for asking this question, and it was inappropriate. So let me just be nice. I don't know what to label this either. Because that was their question. What do I label that? I don't know. What do you label it? The labels I've given to you are not set in stone. Yes, normal force and tension are real things. Friction is a real thing. These are forces, and they have particulars, but sometimes it's just a force. That's why the textbook puts everything as just a capital F. They're all just forces. They all behave the same. AP is not trying to see if they can trick you into using the wrong letter to describe a force. That's not their goal. At the same time, what is the best possible force of the list of the ones you have to describe what's holding the pulley in place? I don't know. I mean, do you know how pulleys are made? I think they're big donuts with a hole in the middle. And that probably means there's like a post going through the hole. And the donut sits on the hole. What force would that? I would call that a normal force, probably. But I could also just say it's the force on the pulley. FP, force on pulley. It's the force holding a pulley up. Don't sweat that stuff. That's the wrong stuff to sweat. Trust me, in a few minutes when I ask you to do one of these on your own, and I walk around and look at your little pictures and they're all wrong, that's what you should sweat, not the labels. So here we go. Net force equals 0 all around. Coordinates, these are one-dimensional. Up positive, down negative. Do I need to do more for this one, or can we move on to something more interesting? Well, something different. Oh, differently interesting. This is an aside, meaning I'm taking a moment to talk about something that is in line with what we need to know here. So let me bring up Newton's second law for just a moment, or try to. The more frustrated I get, the harder I push. Eventually there's going to be cracks all over my iPad here. That's not going to be good for me. That will be a bad day. I guarantee you that'll be a bad day for all of you, and likely for me too. But I you know, misery loves company, and you're the best company I've got. So if net force equals ma, then if we look at the right side of this, this has got to be kilograms times meters per second squared. That has to be the units. No conversation about a new topic would be finished if we didn't at least address the idea of units. And so this must be the unit of force, since the left side is force. So we have a name for this. We call this a Newton. And I will always use capital N for newtons. But kilograms meters per second squared is the unit of Newton, of the Newton. That's not really why I'm taking an entire page to do this. Because some of you are new to physics, you need to really understand something. We are in the MKS system, which means the only units we have are meters, kilograms, and seconds, which you might think sounds, well, no big deal, there's only 3 of them. You're right, there's only 3 of them. Every one of those is a unit we use in physics, and each one of them represents a different measurement, and one of them represents 2 different measurements. And all of them, or some of them, have names. You see, even though it's only the MKS system, we keep rearranging them in new and interesting ways. So, a joule. I know you've heard that word before. This one doesn't have a name, but it's for angular momentum. This one is just for regular momentum. It also doesn't have a name. And this one is for moment of inertia. It does not have a name. But this is the watt. And, I mean, a joule, if you don't know this already, is a Newton meter. But torque is measured in meter newtons. This one is a joule. This one is not. Oh yeah, and a watt, well, that's a joule per second. Do you see why I'm taking an entire page to talk to you about units? Physics is all complex units, and some of them have names and some of them do not. I don't spend a lot of time with dimensional analysis, but if there's one thing I can assure you, it's that at least this is something you can memorize. This is all something that you could memorize. So I would start here. Memorize what the units are for the force. There are other units for force. The English standard is the foot. Is the pound. We don't use it. There's also other ways force can be used. Pressure uses force in it. So although the English standard unit for pressure is PSI, pounds per square inch, the metric is Pascal, which is Newton per meter squared. We don't do pressure much in here, so I didn't list it as one of these complex units, but these are all different things that end up showing up in here. One more thing. We're going to do what is perhaps the easiest Newton's law question there is. I have a box, mass, let's go with mass M, and I drop it. Is this a first law problem or a second law problem? Second law problem, sure. So the net force will equal MA. I take my box and I reduce it to a dot. Is there any fundamental force acting on my box? Yep, so I will draw an arrow downwards acting on the box. And I'll list this as the weight. Any other forces acting on the box? Unless you're told there's drag, then no. So we're gonna stick with this. This is the net force acting on the box. I'll make downwards positive. Okay, so I will apply a coordinate system. And let's see, I'll apply a coordinate system. I will attempt to apply a coordinate system. We'll make downwards positive y. So now add up all the forces, set them equal to MA. I will have weight equals MA. Here's the point I'm trying to make with this example. This is not an example that's really complicated. It's to demonstrate something. When we drop something near the surface of the earth, what is its acceleration? It's the acceleration due to gravity, 10 or 9.8, or g. From this point forward, we will define the weight of an object as mg. So whenever weight is a part of your problem, you can substitute in mg in order to calculate the size or the extent of the weight. That is going to happen every single time you do one of these, so be prepared. Now, today's example. After all of that, this is our first real example. And we're going to start getting into problems that I think are more reasonable, meaning more of my expectation of what I think you should be able to do. Let's imagine I have a box, and that box is experiencing a force of 100 newtons at an angle of 30 degrees from the horizontal. Let's say it is a 15 kilogram box. So some kid is just pulling a box along the ground. The box is moving at 1.5 meters per second to the right. Okay. I would like you to analyze this situation. In fact, I want you to go a little bit further than just analyzing it. We know things now. I think you can tell me the size of the frictional force and the size of the normal force in newtons. That's what I would like you to do, please. Now, this is our first real example where I'm asking you to apply and go through all of the steps. There are some things in here that are new. Let's see if you can do the stuff that we've done that's old, meaning the last 2 days I've been working on trying to get you through a set of procedures that should get you to a point where you can analyze this problem. So draw a free body diagram. Let's start with that. Let's see what I would have done when I say the same things out loud. This is a Newton first law problem. So I'll set net force equal to 0. I'm looking for balance. I'm going to reduce my mass to a dot. I'm going to start by considering any fundamental forces acting on the object, of which I think there is one. I will draw an arrow downwards, and this arrow is going to represent the force of gravity acting on the object. It is 150 units long. I'm calling it the weight. The object is in contact with a surface, the ground, and the ground must be pushing perpendicular to the surface. I don't get a choice in the direction I draw this arrow. It must be drawn straight upwards. But I'm not going to draw an arrow that is the same length as the weight, because I know that there's another force acting on the object that also has a portion of it upwards. And I need to have balance up and down. So I am anticipating another force that is slightly upwards in the future, which will mean the ground is not pushing up with the same amount of force as gravity is pulling down. I'm anticipating that. So my normal force has been reduced in anticipation of what's coming next. The kid's pulling on the box at an angle of 30 degrees. Whether you want to call that tension or not doesn't really matter. It's a 100 Newton force, though. It should be 2/3 the length of the gravitational force, because we know the gravitational force is 150. So I'm expecting another arrow that should be about 2/3 the length at an angle of 30 degrees, like so. It's amazing the number of you who drew this horizontally. I mean, quite literally amazing. But it happens every year, and I don't know why. But I even tell you, it's drawn at an angle and gave you the angle. All you have to do is draw in what you're told. I would call this tension, but you could call it an applied force if you'd like. But lastly, at least nobody really made the mistake here. If you drew it in, almost everybody drew this in correctly if they drew it in. A few of you drew it pointed forwards, but no, the frictional force is attempting to stop the object from moving to the right, so it should be drawn to the left. And I made a reasonable attempt to draw this length, the same length as this portion, the sideways portion, so that there's balance left to right and balance up and down. This is the free body diagram I would expect it to have seen from you guys. Do you see? I went through the series of steps. Now, take 60 seconds. You made mistakes. Write down your mistake. What did you do wrong and why or how are you going to correct it in the future? I don't have that answer because there was a lot of different mistakes out there. All right, time she is moving. So we go on to step 3, apply a coordinate system to this problem. This picture is the free body diagram. When you are asked to provide a free body diagram on the AP exam, you should stop here and not do anything else. Often on the AP exam or on my exam, I will state to draw your free body diagram and I'll give you a place to do so on your test. And I will also go on and say there can be no component vectors in your free body diagram, just the forces as they act on the object. What we're about to do is in violation of that, because the free body diagram is here to help us solve the problem. So you might need a second diagram to do work on when you're dealing with your test. Does everybody understand? I'm going to apply the coordinate system in this case, and it's not accelerating. So my first priority I can throw out, which is to draw the x direction, the direction of the positive acceleration. But I can draw a coordinate system that is lined up with the majority of the forces, and so that's what I will do. I'm going to line up the, I want to use a different color. I'm going to line up the coordinate system in such a way as to be aligned. I want to line it up with at least the 3 forces that I can. So there's the positive x direction. And the positive y direction. I notice that I have a force that is off axis. Well, step 3 requires part C to deal with all off-axis forces by breaking them up into their component vectors. Component vectors are 2 vectors at right angles that replace the original vector. We did this with the wind and the boats on the water. Do you guys remember all that? That was in anticipation of doing this. So I'm going to start by creating a right triangle that is wrapped around the 30-degree mark. Now, folks, there's nothing that drives me more crazy than watching a students terribly destroy this portion of the problem. It's a right triangle. This is one component, this is another component. The right angle is going to be on one of the axes. In drawing it the way I have, I'm going to call this the tension in the x direction and this the tension in the y direction. My job now is to use all measure of trig that I know to figure out how much of that 100 newtons is in the x direction and how much of that 100 newtons is in the y direction. And based on the fact that it is 3:15, I need to move quickly, and so do you. Now, once I've drawn the triangle in, generally, I don't have trouble with students figuring out sine and cosine. The trouble tends to be with students having to draw this triangle in themselves and do it on their own. So I've done 50% of the work, and it's the heavy lifting. This is where I'm like super patient, waiting for everybody else to do it, but go on, sine and cosine. It's not rough. And since I chose 30 degrees, you should have those suckers memorized by now. Can I move on, or am I still waiting? Now, I said this, but you may not have internalized it. So let me say it again. When I break up my force into its components, the components take over. Meaning what I really have here isn't the drawing on the right, which shows a bunch of different forces. It's a much simpler drawing. I have a reduced drawing that has forces like this. A normal force, and tension in the y direction. I have weight, 150 newtons. And I have tension in the x direction, 87 newtons. And I have friction. If you do this correctly, what you really now have are two one-dimensional problems. The components take the place of the vector that was there before, giving you a problem that is 100% horizontal and a problem that is 100% vertical. I can now apply Newton's law because my rules are all one-dimensional. So net force in the x direction equals 0. That will be 87 minus friction equals 0. Net force in the y direction equals 0. That will be 50 plus normal force minus 150 equals 0. We generate two relationships that may be able to be used to solve for the unknowns. And in this case, yes, they can be used to figure out the frictional force and the normal force. All right, still trying to hang with some pretty straightforward stuff, but any questions about this? Yep.
Do you require to make a second diagram, or can you just place it on the one you already have?
You can't place the components on the one that's being graded.
Yeah.
But if we're talking about homework, you can do whatever you want. All right. Here we go. I have another one for you. And just to be clear, you guys are right now doing all the same stuff that AP1 is doing, but yours changes dramatically in a day. Theirs stays about this level of difficulty. Same box, 15 kilograms. I'm gonna have a rope that is perfectly horizontal, holding this box in place, and another rope that is 60 degrees to the vertical, holding the box in place. The box is not moving. I would like you to find the tension in the left cord and the tension in the right cord. I'm not going to do this one. I'm going to put the answers on here in just a minute because the bell will ring in 4 minutes and that won't be enough time for me to do it. You should do it. Okay? This problem is very much in line with what you just did. See what you can do with it, please.